Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture of this course titled Robust Control. So over the course of the last few lectures, we've been trying to look at these controllers that stabilize a plant in a closed loop configuration, and we've been trying to characterize all these controllers, because just getting one controller that stabilizes the plant may not be good enough for the simple reason that we often desire more out of the controller than just the fact that it stabilizes the plant in closed loop. We might also desire some performance metrics to be optimized, right. So therefore, we need to search over a whole family of controllers rather than a single controller. So in today's lecture, we shall build on the pieces that we have laid out in the preceding few lectures, and we shall give you a characterization of all possible controllers that stabilize the plant, and we shall see how beautifully all of those results that we have proved in the previous lectures will all come together. Okay. So let's just reiterate, and just for the sake of continuity, let me redraw the diagram with which we started this discussion. We showed you that if you have a plant, with that general configuration W, the Z, the U and the V and all those signals, then it turns out that we only need to worry about the G22 block, right. So we can forget about the Ws and the Zs, we can just concentrate on the G22 block, right, which is basically the response from D1 D2 to V1 V2 in a analogous diagram, and that analogous diagram is what I am going to draw for our reference again today. So we showed you that we cooked up this artificial system studying whose input output stability is tantamount to studying the internal stability of the original system. That was our goal throughout. Okay. So this is where it comes to. So these are the two noise or disturbance signals that we cooked up. This then was our K, which fed back nicely over here, right. So we showed you that if you can just design this K so that the map from D1 D2 to V1 V2, this particular transfer function was stable, then it turns out that this same K would serve to stabilize, internally stabilize the original configuration with which we have familiarized ourselves by now. Okay. So now, again, how do we characterize, how do we generate a whole family of such stabilizing controllers? So just to motivate this discussion, let us just look at the scalar example, the scalar case when you have a single input, single output system, a single transfer function. So suppose the G22 of S is given by some such transfer function, a rational function, okay, and let x hat s y hat s in RH infinity be such that we have x hat m hat. Of course, we are dropping the s argument here, but remember that these are all functions of s, of course. So, this is the Bezout identity for the scalar case, right. So, we will always have this co-prime factorization, provided that this of course nothing that is cancelling out, that is a given, right. So, it is co-prime. So, this n and m are co-prime, and therefore, this co-prime factorization exists. Let me just sort of clarify and mention it. It is coming due to the Bezout identity, yeah, co-prime factorization. So, this is Bezout's identity, just to refresh your memory. Okay. So, now notice what can we say about the transfer function, that is what can we say about this scalar transfer function that is embodied in this particular relation. Yeah. If you focus your attention on this d1 to v1. So, essentially we know in the scalar case, this is from preliminary courses on control systems, that we know that if you want to find out this transfer function, well, in what order you multiply these blocks now do not matter, because it is scalar multiplication after all, which is commutative. Point is that d1 to v1, the forward path is unity, yeah, and the feedback path is g2 to k, right. So, it is you can just see that readily, that it is going to be this 1 minus k g22, right. So, let me write that down. You can see that v1 v2 is equal to 1 minus k g22. So, let me write that down as a scalar transfer function, 1 by 1 minus k g22. Okay. Let us say you want to find out from d2 to v1, right. So, d2 is injected here and here is v1. So, in the forward path you have k. So, this is going to be k upon 1 minus k hat g22 hat. Now, similarly, if you want to find out from d1 to v2, in the forward path you have g22. This is g22 hat upon 1 minus k hat g22 hat, and similarly from d2 to v2. So, d2 to v2 you have k g22. Right. This is what this transfer function entails. Now, if you just pull it out, you can see that you can have 1 minus k hat g22 hat, this is 1 k hat g22 hat k hat g22 hat times d1 hat d2 hat. So, this turns out to be the transfer function. Now, after all, what is this controller k? Suppose, here is the deal, suppose I choose my controller k hat to be equal to y hat of s upon x hat of s, where how do I get this y hat and x hat? And this is very interesting, because you see what I am discussing in the first few minutes of today's lecture, in the rest of this class today, the rest of this lecture today, we shall be just pushing the same idea for the matrix case. So, although the proofs are going to be rather more involved, but if you understand what is being done here in the scalar case, you have actually grasped the sense of all that is there to the design of a stabilizing controller, right. So, please try and understand what is going on here. What we are saying is, look, I am given a G, out of which I pull out this G22 block, which is what we have been doing over the last few lectures, right, and we have been focusing our attention on this particular block, this G22 and K. And then we say that, look, if this G22 is has a co-prime factorization, then by the Bezout identity, this following result is going to be true, that x hat m hat minus y hat n hat is equal to 1, yeah, that is the GCD. The GCD has to be just 1. Now, we look at explicitly what this transfer function is, and we say that if this transfer function has to be stable, then each component of this transfer function must be stable. If each component of this transfer function is indeed going to be stable, yeah, then what sort of a controller will do that? And I am proposing that this is the controller that does the trick. Once you have understood this, you would know exactly what to look for in the multivariable case. So, what are we saying? Suppose you choose this as the controller, then what happens? You see immediately it follows that 1 minus k hat g22 hat turns out to be nothing but 1 minus y hat over x hat times what is g22? Remember that g22 is n hat m hat, n hat upon m hat. So, this is nothing but x hat m hat minus y hat n hat upon x hat m hat, right. But by the Bezout identity, this numerator devolves to just unity. So, this is 1 over x hat m hat, and we are done. So, now if I plug this back in and I write each of these terms in this particular expression, this k hat and g hat in terms of the x's and y's and the n's and m's, what does it turn out to be? Well, quite simply it turns out to be v1 hat v2 hat is nothing but x hat m hat. You can check, yeah. So, k hat is y hat by x hat into x hat m hat, that is y hat m hat. Similarly, g22 hat is n hat by m hat. So, n hat by m hat into x hat m hat, yeah. So, n hat or rather x hat n hat, the order does not really matter here, it is seesaw after all, x hat n hat, and finally the last one has, well, yeah, it is n hat y hat by x hat m hat. So, it is just n hat y hat n hat times d1 hat d2 hat, yeah. This is all there is to it. Now, notice that each of these individual components here, this for instance, or this, or this, or this, yeah. What do I know about each of them? They all belong to RH infinity. Therefore, it turns out that if I have managed to design a controller such as this, which is basically nothing but generated from the plant's co-prime factorization itself. So, all I am saying is you give me a plant, I am going to get its co-prime factorization, and in terms of the factors that appeared in the co-prime factorization through Bezout identity, I am going to spit out the controller. That is all the information that I need about the plant, right. So, this is exactly the idea that we shall be pursuing throughout today's lecture. But then again you might say, well, look, you promised that you will give us a whole family of controllers, but now you are just giving us one unique controller. It is as if there is something very special about this controller, but that is not really living up to the promise, right. So, what is going to be the characterizing feature, the characteristic feature of every such stabilizing controller? So, here goes. Notice that if you start with, start with the fact that x hat m hat minus, of course, in the scalar case it is very easy. This is the Bezout identity. What I am going to do is I am going to add and subtract a common quantity add and subtract a common quantity yeah. So, I have just added and subtracted this thing in common, nothing special, right, no big deal. Now, if I take m hat common out of this, what am I left with? I am left with x hat minus n hat q hat, and from this latter, well, if I take n hat common, so I can flip around the positions of n and m here because of course it is scalar multiplication. Then I get y hat minus q hat m hat, or m hat q hat, and it is still going to be equal to unity. But look, what am I deriving out of this? What is the big deal about this is, yeah. Now, suppose you call this whole thing as x double hat and this whole thing as y double hat. Yeah, this also satisfies the Bezout identity, right? This also satisfies inequality, and therefore, if someone says that, well, I want to choose my controller not as the ratio of y hat and x hat, but as the ratio of y double hat is to x double hat. By the same argument, not even argument, by the same line of reasoning that we have presented here, it turns out that even this will be a stabilizing controller. But what is the parameter that I can now play around with? It is this q hat. So, suppose I choose this q hat to be in RH infinity, yeah, it turns out that even this is a stabilizing controller. So, now I am saying that you play around with this q hat, choose any arbitrary q hat in RH infinity, and your controller that you will then land up with turns out to be of the form, of course, as y double hat I can generalize it and I can write it down as y hat minus m hat q hat upon x hat minus n hat q hat, where q hat belongs to RH infinity. And bingo, for the seesaw case, we have actually parameterized all possible internally stabilizing controllers for the system in closed loop, right. So, therefore, you choose different, you make different choices of q hat and you end up with different stabilizing controllers. Now, which particular q is going to be your best possible choice depends on what sort of performance parameters you are going to try and maximize or optimize, right. So, this at least gives you a wide array of choices. It turns out that in the remainder of this lecture today, we shall do actually more than just generalize this or extend this to the multivariable case. We shall show that not only is it a fact that by playing around with this q hat, you can generate different stabilizing controllers, but quite startlingly and surprisingly, all possible stabilizing controllers in fact are representable in only this form. So, if I give you a controller that essentially stabilizes that plant in closed loop, then it must belong to this particular parametric form, so much so that this has got a name and it is called the Youla Parameterization. Okay. So, you can look this up in standard texts and you find this Youla parameterization. This parameterizes all possible stabilizing controllers. So, not only is this going to generate a family of stabilizing controllers, but all possible stabilizing controllers must belong to this family. Yeah. So, it is like an if and only if kind of a condition, necessary as well as sufficient. Yeah. So, let us get started with how we can extend this to the multivariable case. Now, before that, let us again refresh your memory a bit with what we have seen over the last 1 or 2 lectures, which is that given any plant such as G22, we will always have a left and right coprime factorization, and we have proved this in the previous lecture, that in that case you must have x tilde y tilde and x hat y hat, which satisfy this particular relationship. This is going to be the key. Okay. So, if you are not sure of this, please revisit the earlier lecture where we have established that this must be true, so that you are convinced that we are not just pulling some arbitrary trick out of the hat. Yeah. So, this is the doubly coprime factorization. This comes from the doubly coprime factorization rather, yeah, where one of them is the right coprime factorization, if I remember correctly, it is the x hat y hat, yeah, that is what we had used, and the x tilde and y tilde were the left coprime factorization. So, given any plant, yeah, we can always get this doubly coprime factorization to satisfy this condition. So, this is a starting point. We are not claiming anything out of the ordinary by supposing that this is true. So, now what we are going to claim in the same spirit as we have done for the seesaw cases, that if you choose a controller of the form u hat v hat inverse, which is its right co-prime factorization, or V tilde inverse U tilde, which is its left co-prime factorization, okay, then this is what we are looking for. We are looking to design this U hat V hat or U tilde V tilde. So, we want to design this such that it stabilizes the system. Okay. So, how do we go about this? So, before we go into this, the first stepping stone towards this result will be, let me mark it out with a single star, maybe I will just keep increasing the number of stars as we push through more and more results. So, what we are saying is the first result, the following conditions are equivalent, and you will immediately see why these are the three conditions that we should bother ourselves with. First condition says that K is input to output stabilizing controller for G22 in the figure above. By the figure above I mean the very figure which I have drawn right at the beginning of today's lecture, which is this figure. Again, this is again not something new, a figure that we have seen so often over the course of the last few lectures. So, essentially this says that if this K is stabilizing this transfer function between D1, D2 to V1, V2, this map, yeah, then what is that equivalent to? That is exactly what we are looking to find out. So, this is equivalent to, hold on, it says that M hat, U hat, N hat, V hat is invertible in RH infinity. So, why is this important? For the simple reason that the first condition is what we are looking to achieve, and the second condition gives us a clue as to what must be met, what condition must be met so as to achieve the first objective. What is that? Look, this M hat and N hat you get immediately from the plant. Then it reduces our job of designing the controller to exactly the following question, that is, can we get U hat and V hat such that this overall matrix has its inverse in RH infinity. If we can manage to do that, then we would have actually designed a controller which input output stabilizes the particular system that we are concerned with. So, the question of this controller design then reduces to just finding this U hat and V hat, which you can pad with this M hat and N hat. Remember, M hat and N hat are already known to us. We can always factorize a plant left or right co-prime factorization, right. So, this M hat N hat is known to us. The only thing that we have to choose are U hat and V hat. Once we have that, it will turn out that this U hat V hat inverse is the right co-prime factorization of this controller that we are seeking. By the same token, since everything must have its dual, like the left and the right co-prime factorization. So, if you are interested in the left co-prime factorization of the controller, then well, you better meet this condition. So, this V hat and minus U hat and minus N tilde M tilde. Again here the M tilde and N tilde will come from the plant itself. So, in this case what we shall be looking to design are these V tilde and U tilde, right. Once we have designed this V tilde and U tilde to ensure that this particular thing is invertible in RH infinity, we would have the controller given by V tilde inverse times U tilde. Okay. So, now of course, this is a good big claim because this leads us quite a long way into our goal of achieving a stabilizing controller, of designing a stabilizing controller. So, then of course, such a claim must also merit a proof, right, because if this is true, then we are well on our way to designing the stabilizing controller, as we can see. But is this indeed true? Once we have proved this is true, then we can have reasonable confidence that yes, we have made some progress. So, of course, we will give a sketch of a proof. What I shall do is, I shall show you that the first statement and the second statement are equivalent, because the first and the third are equivalent can be proved exactly in an analogous fashion by just considering the left coprime factorization instead of the right coprime factorization. Okay. So, I shall only invest my energies into showing you that the first statement implies the second and the second implies the first. You can take it as an exercise to prove that the first implies the third and the third implies the first, in which case of course, by transitivity of this implication relation, yeah, the second and the third will also be equivalent. Okay. So, let us see how we go about proving this. Consider that we have m hat u hat n hat and v hat. This is equal to minus I 0 0 I m hat minus u hat minus n hat v hat times minus I 0 0 I. You see, this relation is true, you can readily check. Okay. But why are we doing all of this? Why are we interested in this relation? Because we are going to now claim that the invertibility of this fellow is tantamount to the invertibility of this fellow, quite simply because this fellow is always invertible. You see, you can treat this fellow as some common matrix at T, and this is T. So, T is obviously invertible, you can immediately see that, right. In fact, you can see that minus I 0 0 I times minus I 0 0 I, yeah, you can readily see that this is equal to identity. Yeah. So, it is its own inverse. Yeah. So, I can even call this T inverse. So, the invertibility of this and the invertibility of this, let me mark that with red so that you can follow. So, the invertibility of this is tantamount to the invertibility of this and the other way round. So, now what we are going to say is, since we are interested in showing that this and this are equivalent, we will instead show that this statement is equivalent to the invertibility of this, because once you have shown that this is invertible, the invertibility of this is a foregone conclusion. So, that is the reason why I wanted to show you this particular relationship. Okay. So, from now on our goal is to show that provided that the first statement is true, yeah, we will show that the second statement being true is tantamount to just this fellow itself being invertible. Okay. So, now notice that we are going to draw this figure, the same figure that we drew at the beginning of today's lecture, we are going to draw this in a different fashion. Okay. Here goes. Okay. So, let us draw this. So, this is D1 as before, then you have V1, but now we are going to split this up, you see. So, this becomes M inverse and this becomes N, let us call this signal here Q, this is V2. So, what does this entail? This says that you are writing G22 as N M inverse, yeah, just the right coprime factorization is all that we are doing here, we are splitting it up. So, same thing we can do with the controller as well. Let the controller first encounter V inverse, let us name this variable P, and then it encounters U until it finally closes the loop. So, I want to be perfectly assured and convinced that we are drawing nothing special here. All that we have done is both the plant and the controller we have taken and written them down in their right coprime form, right coprime factorization form. Yeah, it is the same old diagram that we have grown so used to seeing and we have used repeatedly. Now, with this diagram in place, what can we write? We may write that, look, M hat minus u hat minus n hat and v hat times q hat p hat is equal to d1 hat d2 hat. Nothing special, I am just writing it in a matrix form. You see, m hat q hat minus u hat p hat, yeah, that is equal to d1 hat, is it not? So, you can just readily check this, right, because you see you can just write the equations down here and it readily follows that, look, you have p being hit by a u, right. So, let me probably I have jumped a step, so let me just clarify that. So, you have d1 plus u times u hat times p, okay. I am just writing the hat notation because now I am going from the operator to the transfer function, okay. So, d1 hat plus u p hat, yeah, this whole thing being hit by m hat inverse leads to q hat. So, now if I hit it with m hat on both sides, what I will get is d1 hat is equal to minus u hat p hat plus m hat q hat, and that is all that has been written here. You see, that is basically the first equation. Similarly, for the second equation also you can see that. So, that is the first equation out here, and similarly if you want the second equation you can write, well, you take d2 hat and added with it you get n times q, yeah, because after all v2 is nothing but n hat times q hat, right, that is v2 hat, and that whole thing when hit by a v hat inverse gives you p. So, therefore, you hit it with v hat on both sides from the left, and what you get, what you end up getting is d2 hat is equal to minus n hat q hat plus v hat p hat. That is it. That is the second equation, and you can now check that this is indeed so as we have written it down here, right. So, nothing fancy. So, let us just gloss over this derivation for the time being. It is not really a derivation, but anyway, if you like to call that, and just focus our attention on this particular relation. Again, let me mark that out with a special box, this particular relation. Yeah, we are convinced that this is true now, at least presented some arguments to you to show that this is indeed nothing fancy, okay. Now, apart from this, what else do we know? We know that v1 hat and v2 hat, these fellows, yeah, they are nothing but, you see, v2 hat is nothing but n hat acting on q hat. So, this is n hat, and v1 hat is nothing but m hat acting on q hat. Is the reciprocal relation, right. So, m inverse v1 hat is equal to q hat. Therefore, q hat being hit by m hat on the left hand side would result in v1 hat, yeah, just what we have done. So, I can just write this as m hat yeah, I think so. So, I am just relating it with q only, yeah, yeah, exactly. So, on either side of q you have v1 and v2. So, that, but that I can write in a padded fashion now. Notice that I can write this as m hat n hat 0 0, and I can pad this with, let us say, q hat and p hat, yeah. am just padding it with this, so that I am keeping the coefficient 0 so that no contribution of p hat comes. But now from this relation what do we get? We get the fact that this is m hat n hat 0 0 times what is q hat and p hat? That is nothing but the inverse of this fellow. So it is m hat minus n hat minus u hat and v hat times d1 hat d2 hat. Yeah, but what does that tell us? Now, if sorry, I think I should have written an inverse here, no? Yeah, sorry, it should have been the inverse, right? Because I am trying to free this up to represent q hat and p hat in terms of d1 and d2 hat. So that should have. So now if m hat minus u hat minus n hat and v hat is invertible in RH infinity, then what do I get? I get that this fellow belongs to RH infinity, this fellow belongs along with this inverse belongs to RH infinity. Therefore, the product of two fellows in RH infinity under that algebra, they will also belong to RH infinity, and therefore I have that the map from d1 hat d2 hat to v1 hat v2 hat, yeah, is also in RH infinity. So that means the second statement is equivalent to the first statement. Yeah. So we have actually proved that this second statement implies the first statement. So all that we now need to do is that the first statement also implies the second statement, and we will be convinced about the equivalence. As I said, the latter part, that first and third and first, that I leave to as an exercise. It is very much in the same fashion, in the same spirit as we have done here. Okay. Now, how do we go about proving the latter part? So, by again our old faithful Bezout's identity, what do we have? We have the fact that x tilde m hat, sorry. So, this is the left factorization minus y tilde n hat is equal to identity, yeah, and already we have seen that m hat q hat is equal to v1 hat, n hat q hat is equal to v2 hat. So, what does this lead us to? Suppose we multiply on the right by q hat. So, then this leads us to x tilde m hat q minus y tilde n hat q is equal to q itself. But now this can be replaced by v1 hat, this can be replaced by v2 hat. So, that we have x tilde v1 hat minus y tilde v2 hat is equal to q. Okay. So, what is essentially the implication of this relationship? Let us try and understand this. This shows us that there is a map from this v1 v2 to q. Yeah. So, what have we assumed earlier? Just recall that by our assumption, the transfer function, that is between d1 hat d2 hat to v1 hat v2 hat belongs to RH infinity. Yeah. But this is very crucial, this observation. This is our assumption that the transfer function, the map that takes this pair of signals d1 and d2 to v1 and v2, not pair of signals but tuples of signals d1 d2 v1 v2, yeah, that is itself going to belong to RH infinity. And now in addition we have this relationship whereby we see, by invoking this Bezout identity, that the map from v1 v2 to q hat must also be in RH infinity. So, if you go about it in this fashion, right, like transitivity. So, the map from d1 d2 to v1 v2
is in RH infinity. The map from V1, V2 to Q is also in RH infinity. Therefore, because these are after all compositions of maps, both of which are in RH infinity, yeah, so therefore compositions of maps in RH infinity would also result in a map that is in RH infinity. Hence, we can say that this entire map from D1 hat, D2 hat to Q hat at least, okay. We will fill out the other part. I will just argue shortly why the other part, that is P hat, yeah, that must also be in RH infinity, but that will require the invocation of another Bezier identity, yeah, but all in good time. So, let us just see. This means that the map from D1, D2, D1 hat, D2 hat to Q hat is definitely in RH infinity, but our entire proof requires that the map from D1 hat, D2 hat to P hat, Q hat must be in RH infinity. So, we also need to show that the map from D1 hat, D2 hat to P hat is also in RH infinity. For that, we similarly apply the Bezier identity to the controller. So, what is the corresponding Bezier identity for the controller? For the controller, we may write that there exist objects in RH infinity such that xk hat, yeah, xk tilde, sorry, that's the k subscript corresponds to the controller, of course, v hat plus yk tilde u hat. Recall the structure of the controller we have drawn here, yeah. So, this uv corresponds to the representation of the controller, is it not, right. So, now we have this is equal to identity, and clearly if we hit this with p on both sides and do exactly similar set of steps, we will come to the conclusion that the map from, just like we have from here, from V1, V2, so I leave that detail as an exercise for you to check suitably, that the map from V1, V2 to P hat, in fact, okay, let us correct this with P hat, is in RH infinity. And once again, as before, you see, by your assumption the map from D1 hat, D2 hat to V1 hat, V2 hat is in RH infinity, and now from V1 hat, V2 hat to P hat is also in RH infinity. So, therefore, the entire resultant map from D1 hat, D2 hat to this P hat, Q hat. So, I can now actually get rid of this in red ink and probably also correct the order in which I have sort of written this, okay, and write that the entire map from D1 hat, D2 hat all the way down to this P hat, Q hat vector of signals, P hat, Q hat, belongs to RH infinity, alright. So, that is an important result. Now, in view of this crucial observation and this red boxed equation that you see before yourself, what does it now tell us? That if the map from D1 hat, D2 hat to Q hat, P hat, okay, let me correct the order there, okay, I will correct it later, but the observation still remains, right. Now, if you want to find out the map in terms of this box relation, you need to just hit both sides of this equality, this equation, with the inverse of m hat minus u hat minus n hat v hat, yeah. So, that inverse is exactly the object that tells you what the map from D1 hat, D2 hat to Q hat, P hat is, right, okay. So, let me make that very warranted correction here. We should be consistent with this. So, this is Q hat, P hat, yeah, right. Now, we are good to go. So, therefore, this inverse of this object, this fellow, let me mark it in some other color, purple color. So, the inverse of this purple fellow, this fellow's inverse is exactly that map, which is taking signals D1 hat, D2 hat to Q hat, P hat, and that must be in RH infinity by our argument, and therefore, the inverse of this purple circled block, this matrix, that is m hat minus u hat minus n hat v hat, must be in RH infinity, but that is exactly what we were required to prove from the very outset, right. And therefore, I would argue that this completes the proof of this particular result. If you want to prove the third part of this, yeah, once again you have to take the other side, the left co-prime factors. We have taken the right co-prime factorization, you have to take the left co-prime factorization. So, that also I leave to you as an exercise, exactly the same set of steps, right. You start with the left co-prime factorization of the plant and the controller, and you will arrive at a proof for the third result. So, we have shown the equivalence of 1 and 2. If you want to show the equivalence with 3 as well, just invoke the left co-prime factorization, and that is all that you require. Okay, it will be a good test for you to check whether you actually grasp the concepts here, right. So, in that case the crucial objects will be these fellows, alright. So, these will encapsulate your controllers factorization, the left co-prime factorization thereof. Okay, we already discussed what these left and right co-prime factorizations are, and therefore we are good to go. And now we will move over to the next object of interest. So, now having laid the foundations for this, we are now in a position to state the Youla parameterization, the big result, to state and prove this big result, that is Youla parameterization. Okay. So, the condition is that the stabilizing controller exists, and this is very important. Okay, let me write it in so much so that let me write it in red. It says if and only if. So, it is both ways, as I said, right. Not only is it that anything that you get out of Youla parameterization is stable, but also anything that is stable, stabilizing controller, must also have this Youla parameterization form. So, it is if and only if there exists. So, let me write that down. There exists Q hat in RH infinity such that K hat is given by y hat minus m hat q hat times x hat minus n hat q hat inverse, which is the right co-prime factorization of the controller, which is also equal to x tilde minus q hat n hat inverse and y tilde minus q hat m hat, sorry, m tilde, is it? Yeah, it should be the tilde. Yeah. Right. So, this is the left co-prime factorization with the two inverses in the left and the right co-prime factorization, that is with the two inverses existing in RP, that is their proper. These inverses that we are cooking up, these are also proper, because then if you multiply two proper transfer functions, you get a proper transfer function. So, this is the big result. Okay. So, of course, this needs a proof, and this proof is what we shall be doing in the remainder of this lecture and wrapping up thereafter. So, again we will give you a kind of a sketch of the proof, not very great details, but it should be good enough to convince you. So, consider that we already know this, right. This we have proved in the previous lecture, I think, that when you have the left and right co-prime factorization of a plant given by the tilde, the left co-prime, and the hat, the right co-prime factorization is what we have used in our convention, n hat x hat. Yeah, I am just going to leave a little bit of space here and you are going to immediately see why. So, this is true. Okay. Now, if I hit it with a matrix and its inverse on the left and right, it is still going to be true. So, that is what I am going to do. Let me use a different color. Okay. Yeah. So, let me hit it with this particular matrix I q hat 0 and I minus q hat 0. You can check that these are inverses of one another and therefore would not matter on the right hand side of the equality. Okay. So, now if I simplify this, I will get the following. I am going to first take these two together and then these two together. I am going to write them down as a product. So, I am going to quickly write that down. You can check the calculations, minus n tilde, yeah, okay, maybe not so quickly as I had thought, minus q hat m tilde, and this is going to be, yeah, m tilde, that is right.
and this is going to be m hat n hat y hat minus m hat q hat, and this is x hat minus n hat q hat is equal to identity. Okay. Having come this far, you see, in order to prove that this second equality is true. So, what is the second equality I am talking about? Let me highlight that again. Yeah, I am talking about this equality. Okay. In order to show this equality, I am going to now look at this expression that I have here, and I am going to look at the 1-2 block, the top right hand corner, the northeast block of this matrix on both sides. And on the right hand side, you know, because of the identity, that block is going to be 0. Yeah, but on this side, what is it going to be? It is going to be this particular row multiplied with this particular column. What is it going to lead to? It is going to lead me to conclude that x tilde minus q hat n tilde times y hat minus m hat q hat minus y tilde minus q hat m tilde times x hat minus n hat q hat is equal to 0, right. So, if this is to be true, what happens? If this is to be true, immediately you see that this you can hit it with the inverse of this on both sides from the left and the inverse of this on both sides from the right. So, you get y hat minus m hat q hat times x hat minus n hat q hat inverse. So, the moment you have this inverse existing, yeah. So, if the first part of it is true, that, or rather these inverses exist, yeah, then you can always see that this equality is going to be trivially true. And on this side you have sorry, what is it? Yeah, x tilde minus q hat n tilde inverse times y tilde minus q hat m tilde. Yeah. So, the second equality is at least well taken care of. Yeah. So, we have this to be true. So, now we have to show that it stabilizes. Yeah. Just showing that this equality, okay, this controller, it looks very elegant and sleek. Yeah, it has a left and right co-prime factorization given by this and this, provided these inverses exist. Yeah, the x hat, y hat, x tilde, y tilde come from the plant itself. So, only subject to your choice of a particular q hat, that is the only thing that you have to choose, because m hat, n hat are just m hat, n hat, m tilde, n tilde are just factorizations of the plant. X hat, n hat, x hat, y hat, x tilde, y tilde, they come from the Bezout identity, the co-prime factorization. So, therefore, the only thing that you are choosing is this q hat in RH infinity, such that these inverses exist, and it turns out you get this controller. But the fundamental question remains, what is the guarantee that this stabilizes the system in the first place? Yeah. So, how do we prove that? This co-prime factorization exists, but what is the guarantee that it stabilizes? Yeah. So, let q hat belong to RH infinity, and suppose u hat is equal to y hat minus m hat q hat, u tilde is equal to y tilde minus q hat m tilde, v hat is equal to x hat minus n hat q hat, v tilde is equal to x tilde minus q hat n tilde. Okay. So, we define these variables in this manner, suppose, right. Okay. Then what happens? From this relation here that we put in, you see this particular relation here that we put in, if we just substitute in terms of the new variables that we have defined, what we shall be getting is, yeah, n tilde, m tilde remain as they are, it is only the new variables that come in. So, what we have is v tilde minus u tilde minus n tilde and m tilde times m hat u hat n hat v hat is equal to I. Yeah. Now what happens? You see this inverse exists and is exactly equal to this fellow. So, by choosing a q hat in RH infinity, what you have done is you have ensured that this fellow's inverse exists, not just exists but also exists in RH infinity. Why? Because this is that inverse. And why must this belong to RH infinity? Because every member therein is in RH infinity. Yeah. So, therefore, of course, this must belong to RH infinity. So, just by choosing that the q hat is in RH infinity, you have ensured that this whole thing is in RH infinity, and this is also exactly by this relation the inverse of this fellow. But what does it mean to have the inverse existing in this? By our preceding result, this means that k hat given by u hat v hat inverse is equal to say v tilde inverse u tilde also stabilizes the system, right, because that is what we proved just in the previous result, that if you have this particular fellow, this m hat, u hat, n hat, v hat, according to the second condition, you see the equivalence of the first and the second condition that we proved, as long as this fellow's inverse belongs to RH infinity, this will stabilize. So, we have seen that at least this Youla parameterization by choosing a q hat. So, what have we seen so far? We have just seen the multivariable equivalent of what we have seen in the first 10 minutes of today's lecture for the seesaw case, for the scalar case. So, we have just seen that if you choose a q hat in RH infinity, you will end up with a controller that indeed stabilizes your system. But now the bigger part of the proof remains, which is to show that not only that this stabilizes, but that this is the only way to stabilize. Yeah. So, every stabilizing controller that you can throw at me must necessarily have a Youla parameterization. Yeah. So, for that we need a little bit more work, maybe we do not have time for that in today's lecture. We shall complete with this proof in the next lecture, and we shall show that indeed this Youla parameterization perfectly captures or encapsulates everything that we need to know about the family of stabilizing controllers. Till then, take very good care. See you all next time. Thank you.